Welcome. My name is Jukka Haho, and I will be your host today's FEA webinar. We are very excited to have all you here today. Our presenter today is Mr. Anson. He is the leading expert in the field, and we are thrilled to have him share the insight with us. Anson, would you like to introduce yourself?
Thank you, Jukka. Hello, my name is Anson He. I'm a technical host today. I have a background in material science and engineering, and I'm particularly interested in mechanical property and behavior of metallic material. I have been working in Vertex Australia office since 2016, and I mainly focus on technical support, trust engineering, and of course, FEA development. I'm looking forward to show you the capability of FEA in Vertex BD today.
Thank you, Anson. And now let's have a quick look to today's agenda. We will start with the Anson's presentation, followed by the special video created with this topic by Anson. After that, we'll open up the floor for the Q&A session. And just a couple of practical notes before we begin. This webinar is being recorded and will be available on our YouTube channel afterward. Also, feel free to submit your questions in the Q&A section at any time during the webinar, and we will come back to those during the Q&A session. Okay, Anson, stage is yours.
Okay, thank you, Jukka. So FEA is short for Finite Element Analysis. So in Vertex BD, trust engineering is focused on the trusses only, and FEA tool opens up the model to the user to analyze any profiles and panels in as long as it's made of light gauge steel and as long as it is a C profile. So in terms of design principle, it uses Euler-Bunod in theory. So every member would have two nodes at each end. And of course, later on when we build up the model, we can build additional nodes along the member. So nodes, each nodes would have 6 degrees of freedom. So 3 degrees of translation freedom and 3 degrees of rotational degree of freedom. Then that makes up our basic FEA model. Then after the solve of the FEA model is finished, we can perform capacity check. So we will apply the buckling rules of light gauge steel profile and then perform capacity check based on the profile capacity. Then in terms of results, we can perform standard FEA solve, which will give us stress, load, and deflection distribution. And also, in the end, we can give capacity check result for every member within the FEA study. So next, let's move on to the FEA demo in Vertex BD. We have prepared a short video. So Jukka, we can play the video now. We will now demonstrate the FEA tool capability in Vertex BD. The FEA tool in Vertex BD can be used to analyze any C profiles in the project. This will include not only the trusses, but also the wall panels or any other structures that are made up with light gauge steel. As long as the cross-section is included in the engineering data, then we can use capacity check to check the capacity for any structures. To get access to FEA tool, first we need to be in the framing model pair, and then right-click in the empty spot and find FEA for beams and frames. Once in FEA module, we need to single out the object to design in the FEA study. For this particular model, I will use this garage door lintel as an example. You can include multiple wall panels, multiple trusses, or any structures for that matter. First, choose the wall panel you want to include in the FEA study and right-click and create new study. We need to click self-weight of profiles so that we can include the self-weight of the profiles into the low combinations. The list of low combinations can be found here. We will just have to select all and click OK. As you can see, this wall panel has been now included in this FEA study. Any profiles that are not included in this wall panel will be displayed in gray color so you don't get confused. First off, I need to connect all these profiles. I will use hinge about transverse axis y as the property of the link because we want to simulate the situation where we have one screw on each side of the flange. In those cases, we expect the profile can rotate in plane about y-axis. After the nodes are linked, you can see they will turn blue, and the master node will be the darker blue big balls, and the lighter blue ball are the slave nodes. Next step, we need to establish the boundary condition of this wall panel. First off, I will fix all the nodes on the bottom track. So we can see that the ground can provide necessary boundary condition for these nodes other than the rotation about the y-axis. We also need to consider the support from the trusses. Before we do that, I want to transfer all the reaction loads from the trusses first. We have a function for that. It's called support reactions. Now the system will transfer all the reaction loads from the trusses. To be able to use this function, we need to have truss engineering done for the trusses because the reaction loads are from the truss engineering results. The load transfer must be unfactored and it will be resultant of multiple different load cases. Therefore, we are importing multiple reaction loads into the current study. It's going to take some time, between 3 to 5 minutes. Now the reaction loads have been transferred onto the top track of the wall panel. You can see the system will add the 3 nodes on the top track and add all the reaction loads. Now we just have to select those 3 nodes. Then I will add y direction translation. So the y translation will be limited for those nodes. This is so that we can simulate the lateral support from the trusses. Now the top track nodes at these locations where the trusses is in contact will not move in the y direction. Next step, I want to add the area load simulating the wind load perpendicular to the wall panel. I have an area load here. So I will select the boundary member, and now you can see the area load orientation. The members which are highlighted are the members that would take the area load. You can choose or unchoose the members which would take the area load using parts function. Now we will just have to define the magnitude of this area load in kilonewton per square meter. The magnitude should be consulted by the engineer and get to the number that is realistic. Remember to consider the wind load coefficient on the wall in order to calculate for the correct area load to simulate the wind load onto this wall panel. Here I will just use 0.4 as an example. For the load type, we will have to select the correct one because later on when we perform the capacity check, the load combination factor will be dependent on the load type. Click OK, and now the system will apply the area load and convert the area load into line load onto each members. We can now click Solve to obtain the FEA result. By default, the system will show us the Vertex stress distribution on the wall panel under the current load condition. Vertex stress is valuable for regular FEA studies. It's usually used to compare to the yield strength of the material so that we can determine whether or not the deformation is elastic or plastic. However, in current condition, because the object of study is light gauge steel and is likely to fail because of buckling instead of yielding. Therefore, the Vertex stress is less valuable in this situation. After clicking this pull-down menu, we can also use different stress plots. For example, axial force. In this case, we have positive values and negative values. The positive values are in compression and the negative values are in tension. We also have torsional moment, bending moment in the y plane, my. So the bending moment in the y-axis is the in-plane bending moment, and mz is out of plane. Shear force is out of plane shear force here in qy, and qz is in plane shear force. Normal stress is the stress distribution when we calculate it for normal stress. Again, it's less valuable here for light gauge steel, but we can still get an understanding of the stress distribution in the current study. Then we have displacement. Displacement will start from 0, so it's always positive. The maximum displacement here for this study is 12.5 millimeter, which is in the center of this lintel. Then we have dy, which is out of plane displacement, and dz, which is in plane displacement. We also have twist force, which will be resultant from the area load perpendicular to the wall panel. Displacement slider allow us to change the magnitude of displacement of the current study. So this is a very handy tool for us to check whether or not the displacement is reasonable. You need to have basic engineering understanding of the current object of study so that you can determine whether or not it is reasonable. In terms of result display, we can not only display color view but also a diagram in the current stretch plot, which is displacement d at the moment. We can see different numbers here which are the exact number of displacement. You can also select it to show, for example, here is an in-plane bending moment. You can see how the bending moment is distributed as well. You can choose different showcase methods to suit your needs to make the display a little bit more clean and presentable. After you are happy about the view, then you can use save view here to save this current view as a result. As you can see, the system will turn the background into white, so the result is more presentable. It will also include this scale on the top left, so the engineer will have an idea of the distribution of the current parameter. I also want to point out that results here are unfactored, meaning that all the loads included in the current study will act on this result at the same time, and none of those loads are factored, so this result cannot be used for capacity check. In order to perform capacity check, we need to go through all these functions. First, we need to define load pattern. In this case, I will include all the loads. I can just simply click on loads in the FEA model tree, so all the loads will be selected. And then I just click OK and name this load pattern OR. So that means all the loads will be included in this load pattern. I will select all these load combinations, so all the loads will be put into this load combination. After doing this, I will define the buckling length. I will take all these tick boxes saying apply between linked nodes. The system will now go through all these connections and consider the property of these connections, then define appropriate buckling length considering the connection. So we have buckling length for Euler buckling about section Y, which is in plane, Euler buckling about section Z, which is out of plane. And then we have torsional and also lateral buckling. For lateral buckling, we have positive Y and negative Y, because we have the outer side flange and interside flange. So the plus Y is the outer flange at the moment, and minus Y is the inner flange. You now see all these lines. They are indications that the buckling length have been defined. Now we can perform the capacity check. In capacity check, the design criteria is exactly the same as what you will have in trust engineering. You will just have to define the deflection limitation. We have an error message here saying the product is not strong enough. And when you highlight this error message, you can see an arrow will point at the location of the error. And the type of failure will also be described here. It says it's deflection design error, meaning that at the location, the deflection will be higher than the limit that we put in. Now the next step is to modify the wall panel structure so that we can make the displacement a little bit less at that location. In order to make structural modification, we need to get out of the FEA module first. We get out into this regular 3D framing model, and now we can make our change to the structure. At this case, I will just copy this web across so we have more webs to take the deflection from the trusses. Okay, it should be in that bay. So copy again. Of course, I need to move this as well. In this case, I will just establish the connection first. Then I will again move this in, so it's 55 mil away from that node. We can check easily, see if they have overlapped. In this case, I'll move it away a bit further, so we'll have a bit more tolerance to work with. Go back to FEA module now. As you can see, the new profile is not included in the current FEA study, and the connection here will also be moved because the profile has been moved. Rather than establishing new contact, I rather just create a new study all over. I just have to name it a different name. So as you can see, we can perform multiple FEA study on the same project, on the same model. So we can investigate the effect of our change in the structure and also the effect of different boundary conditions. So I will just repeat the boundary condition definition as we did before and transfer the reaction loads from the trusses again. Note that this new profile will be included into the current study as well. And a new FEA study is on the right of the FEA study tree. After the load transfer has been done, now we just have to select those three nodes again and establish the lateral support from the trusses. Okay. Now we'll just add area loads into the FEA study as well. Make sure that we input exact same wind load as our first FEA study. I'll quickly just click solve so that we can have a look whether or not the displacement is reasonable. As you can see, the FEA solve is actually pretty quick because we only have bin members in our FEA study, so the solve is nice and easy. Now I will just create that same load pattern including all the loads in the study. Then define the buckling length. I can use also this by members function to define the buckling length. We can now perform capacity check. For the deflection limit is some good values that you should consider your engineer. In this case, we will just have default values from 1170. We still have a calculation message with the error saying the deflection design error. So deflection design error have been moved. Previously it was at this location and now it's at this location. Okay, so apparently this truss also make the top track deflect a little bit more than desired. So we will close this and make further adjustment as well. Considering this truss is right next to this vertical, I will just copy this vertical to make another one side by side with this current one. So essentially we have a double stud at this location. And also I will have to move this web so that it is not overlapping with that vertical. Now I can go back to FEA. Actually, now I don't have to create a new study because I didn't move this web by a lot. So I will just add this. Make sure that you have selected the correct FEA study. In this case, it will include also this web member. So I will add this additional member I added into this study. So I'll right click this member, add to study. So now it's also blue. So what needs to be done is that I will have to establish the connection between these members again, because the new member is not yet connected to the current study. I'll just use the default connection node property because it was the same as all the rest. Okay, so the new nodes have been connected. Next step, I will also need to define the buckling length for this piece. So I click by members, highlight this piece. Okay, so now this piece is within the model. I'll double check the load areas first. So yep, so these webs, they will not take the area loads. The area loads will be taken by the distinto piece and the top track. So this is okay. I'll just quickly perform capacity check. Right, so there is another error saying that we are failing by deflection design error again. So this is a bit of an iterative process. The system will check for deflection for the top track at different locations, and the error will just point at the location where the failure occurred. Even though there are multiple locations of failure, it will just point at the location where it failed most. Alright, so I'll copy this vertical. I basically just will do the same thing as the previous one. And then move this piece. Alright, get back to FEA and include that new member into the FEA study again. Add the study. Because I moved this piece as well, so I better just do the link again so it will have its own master node. Now you can see it has its own master node. Alright, so define the buckling length for the new piece and perform capacity check again. One more deflection design error, so we can see it's from this start. Okay, so let's go OK here. I will copy across this stud and make it a double. This truss is taking a lot of other trusses load as well, so that's why we need a double stud at this location. This is why FEA is valuable, because it can point out where we can optimize the structural design. Now what I have to do is I will have to establish connection between the new added member and the other members in this current study. System will highlight the first study by default. Just remember that you select the most recent FEA study. It's also probably a good idea to create new study so that you can limit the chances of error, but of course that would take a little bit more time. Therefore, it's a balance that you have to manage yourself. All right, so that piece is now a part of FEA study. However, I will need to re-establish the area load. I will go to property of the wind load. The reason for that is that the new piece will also take the area load. So I need to select parts. Also highlight this piece. Go OK. And let the system to redistribute area load, including that vertical as well. Don't forget that you also have to define the boundary condition for this node, so that is also supported like the rest. Because we defined area loads, now the load patterns will have to be updated. I will first delete the previous load pattern and establish a new one. Again, select all the loads again and select all the load combinations. Alright, so now we can do capacity check. Alright, as you can see, we don't have that error message anymore, meaning that the current wall panel will suffice the capacity check. To double check, we can select all the members, right click and get to capacity summary report. Now you can see design is adequate for all members, and you can double check all the capacity check results, including deflection, which was the mode of failure in the beginning.
Thank you, Anson, for a fantastic and very detailed presentation and video. Now we will move on to our question and answer session. We don't have any questions yet, so we maybe wait a couple of minutes, 1 minute, that if you have something to ask, we are now ready to answer your questions. You can submit them to Q&A section of the webinar user interface. So far, we don't have any questions. Some information about this video and where they can be then find later on. We have that kind of YouTube channel, Vertex BD Building Design Software, and there's the webinar playlist. You can find the latest webinars from there, and that also this webinar will be there soon. Now we do have one questions. Can the deflection error in the lintel not to be fixed with adding a lintel plate?
Okay. Right, I can see the question.
Okay, Anson, have you answered about this?
Yeah, so the question is about how to fix this deflection error, and the question is whether or not it can be fixed by adding a lintel plate. That is an excellent question, because lintel plate is a very commonplace way of reducing the deflection of a lintel, and we understand that a lot of users will use this kind of solution. In FEA, if you want to simulate effect of lintel plate, we need to play with the nodes so that the top track and the lintel header will be connected as one piece, so simulating the connection of the lintel plate. However, we do not have a profile per se to simulate the lintel plate itself. So short word is that yes, we can do it, but it will require some modification to the model itself.
Okay, thank you, Anson. We don't have, okay, now we have another one.
Yeah, question is, can we analyze structures with additional sections, like a square 120 by 120 millimeter used for the uprights, or an H-beam used for the transfers for large openings like big doors or windows? So this relates to structural steel use in light-gauge steel buildings. In FEA, we can perform standard FEA solve for the structural steel members, meaning that we can look at the stress distribution, the force plot, and deflection of the structural steel members. So yes, that is totally workable. However, because we are working with Australian Code 4600, and it did not give any provision for calculation of the capacity, so we can't do a capacity check with the structural steel. Therefore, we can only perform the standard FEA solve. And having said that, that actually provides very good information because we have Voronoi stress and normal stress distribution, and we can use those numbers to compare to the yield strength of the structural steel. But just remind you that you have to work out a factored load by yourself and then apply the factored load into the FEA model separately, so you can do the capacity check that way. Let's see.
There is a question about the building size.
Yeah. Okay, I'll enlarge it. So I also find another question about, is it possible to design a warehouse? Yes, so warehouse is actually what we can use for FEA, because in regular truss engineering, a warehouse is very difficult to design using truss engineering because you don't have the defined below slope and maybe sometimes above slope, and also the wall might be integrated with the trusses as well. So FEA would be basically the only way you can do it with in Vertex. So yes, you can use it to design a warehouse. I would recommend that you do not do the whole warehouse, but just single out maybe one piece of the truss with the wall and then apply the load there, because it will make it simpler and quicker to work with. Yep, so that's the follow-up questions. Let's say we have a 24-meter clear span. 24 meter is a very large span if we're looking at light gauge steel houses. So I really doubt if it will work, but we can definitely add into FEA study and at least explore whether or not it works and see what kind of failure mode we would have.
Then there was a question about do you have the experience of the European and Italian regulations and calculations? We support actually Eurocode with UK annex. That's what we support.
Yes, correct. Yeah, so basically in FEA, other than the standard FEA solve, we perform capacity check. And when we do capacity check, we have a section where we can change the building code we use. Currently, we have Eurocode and Australian code and the China building code as well. And the question about next is, what about build-up beams and columns? Build-up beams and columns, I believe, is also related to like warehouse. Like I said, for the structural steel, we will have to perform only standard FEA solve, meaning that we can't use capacity check in Vertex BD. But after you perform standard FEA solve, you will be able to see the distribution of stress and also deflection. So you can compare to those to the limits and the capacity of the beam itself.
Okay, I think all questions are now went through. So thank you for your excellent questions and participating today's discussion and webinar. Before we conclude, I want to let you know about the next webinar. It will take place October 21st at the same time, and you will see the topic and date on the screen. And if you found this topic interesting and would like to order this feature and simply learn more, please contact our sales team. They will help you. And you can find their contact details on our website, which is displayed on the screen, this web address. From here you can find it. So thank you again and joining us today.
No worries.
Have a great rest of your day, and we hope you to see again at the next event. Goodbye.
Thank you. Goodbye.